So guys, we're going to go ahead and get started. Today we're kind of doing a little bit of an addition to what we worked on yesterday. Yesterday we just talked about the basics of vectors. And today, guys, we're going to throw in how you break them into your components. And we did this a little bit yesterday. But we're going to review this again. We're going to hit how we add vectors. And then we're going to do a more complex problem of how we add vectors using components. Okay? So, guys, kicking it off, if we have vector A here, and we worked on drawing these yesterday, if it has a magnitude of 56 newtons, and it has a directions of 23 degrees north of west, we would draw that vector by going west, drawing a west line, and moving 23 degrees north of west, and then drawing a vector that points out in that direction with a magnitude of 56 newtons. Pretty simple, pretty straightforward stuff. We worked on that yesterday. Now, if you want to break that vector into its x and y components, then what we would do is we would draw these two components like I have drawn right here. This would be the x component, which, by the way, guys, is pointing in what we would call the negative direction, right? And then we'd have the y component going in this direction, which is pointing in what we would call the positive direction. Everybody kind of see that? Okay. Now, how do we break these into our components? Well, we looked at trig over the past couple weeks, and yesterday we reviewed it. Okay, this would be the x component right here, so we're going to move over there and do that one. We're going to do the y component right here. Let's go ahead and start with the y, since it's right in this area. What side would this be comparative to this angle? Well, we should have what? Opposite and hypotenuse. So which trig function we're going to use is going to be what? Sine. Okay. So really what we would have here is sine 23 degrees equals AY, because we're calling this vector A, that's going to be its y component. It's going to be opposite AY all over hypotenuse, which is 56. Everybody see that? Okay. Now to solve for this thing, how would we solve for this thing? It's really simple. We plug sine 23 into our calculator. We got to divide. We're dividing by 56. So we multiply both sides by 56. And AY is going to turn out to be sine 23 times 56. And then, does anybody have that on their calculator that could help me with that?
21.880.
21.880 newtons. That's my AY component. Okay, so that's the y component. And guys, because it points upward, we're going to make it a positive. Everybody see that? Pretty simple stuff, right? Okay. Now, we're going to bounce over here to the x component. So we're going to call this AX, or the x component of vector A. And if we wanted to find that, guys, we have what? Adjacent and hypotenuse. So that would send us into that cosine function of 23 degrees equals adjacent, which is AX, all over hypotenuse, which is 56. Right? Now, when we solve that, we would come up with something like AX equals cosine 23 times 56. And somebody on their calculator could probably hopefully throw that at me.
51.548.
51.548. Okay, we got some agreement on that? Okay, all right. So guys, that is the x component, but if we look at it, it's pointing in which direction? Okay, that kind of the left direction, so we're going to give it a designation as negative. Okay? And the reason we're going to do that, if we pop over here really quickly, when we add this vector, it's going to have a positive y component and a positive x. This one here is going to have a negative y component and a negative x component, and when we add them together, we're going to have to take that into account. That's why we always take into account that direction. Okay? Can we all break vectors into components, you think? Okay.
How does that work that it's 56 newtons?
Okay. Well, guys, this is a good question. Okay. What we could do, because we know the Pythagorean Theorem, and we know right triangle trig, right? We could take this number and square it. That would be what? A squared plus B squared should equal C squared. And if you did that, can anybody do that real quick on their calculator? Throw in 51.548 squared plus 21.880 squared. And then take the square root, and hopefully we end up somewhere right around 56.
Yeah, 55.999.
we did some rounding here, so we're not going to be exact, but it's right on, okay? Good question, okay? Now, guys, if we move on to this next little piece here, we didn't talk about it a ton yesterday, so I want to make sure you get it. We always add vectors head to tail, okay? So if we look at this right here, when I say head, I mean the arrow part, tail is the origin part, okay? So if we look at this and we say, vector A is a vector that is 25 meters per second, 45 degrees north of east, and vector B is 25 meters per second due east. And guys, we could talk about this as maybe this is our airplane and we're flying this direction, and then we have a wind that's coming at us from this side. What's going to happen to our direction of our airplane? Well, guys, if we do that, we take vector A, which you can see I've drawn here, vector B, which I've drawn here, and you'll notice I put vector B, its tail, touching vector A's head. So we would say we add this vector head to tail, and that's how we would add the vectors. Now, if we were in just conceptual physics, we probably wouldn't use the trig, we wouldn't use that sort of thing. We would draw these to scale with a protractor and a ruler, and then we would come in, and guys, I'm going to draw this in red. If we add those two vectors, we get what's called a resultant vector, okay? And the resultant vector is going to go from the beginning up to the end, and that would be our resultant vector. We usually indicate that with a capital R, okay? So I'm just going to come in and we'll put resultant, which is basically the sum of the two vectors, okay? Now, guys, you guys are all understanding that because we have certain directions, we can't just add stuff together. We can't say 25 plus 25 is 25 because they're going in different directions, right? So that's how we take that into account, okay? Now, what we're going to do in the next step is teach you how to add these vectors in a way that we can come up with a resultant vector that works really easily. Now, some of the kids at this point are going, well, if we have two vectors, we could use the law of sines and work some things like that. That can work with limited amounts of vectors, but when we move into multiple vectors, we have to have a different technique, which I'm going to show you right now. Okay? Cool. Forgot we left this up here. I'll erase this real quick. If you look at this next part, what we have is we have three vectors that we're trying to add together. So if we're adding these three vectors together, we have vector A, which you can see is 15 meters, so I've drawn it pretty much to scale. It's 32 degrees.
Should say east.
You know what? We got to go east of north. Let's set that up, okay? Because this is north, we're moving in the east direction. So we're going 32 degrees east of north, and then we're going 10 meters due east, and then we're going to go 8 meters, 25 degrees west of south. Okay? Now that's going to take you guys just a second to go ahead and draw that up in your notes. So I'll give you a second there. While you do that, I'm going to go ahead and draw. I'm going to try to draw each of these X and Y components. Okay. And then we'll go about adding these vectors. So guys, what we're going to do here is when we add vectors, that's all we're going to do is break them into their components, into their X and Y components, and then we're going to set up a problem that looks like this. We're going to say the X component of the resultant vector is equal to all of the X components of these vectors added together. The Y component, I'm trying to give myself space here. The Y component is going to be equal to all of the Y components of the vectors. So in this case, this is the Y component of A. There is no Y component of B. And then we have a negative Y component of c. And so our resultant vector, our x components is going to be all the x's components added together, and the resultant vector y is going to be equal to all the y components added together. Okay? And if I can, I'm going to draw this resultant vector in purple. That'll kind of hopefully help you see that. Okay? So I'm going to draw this resultant vector moving up here and going to there. That is going to be the resultant vector. Okay? Do you guys see that? Now, guys, the resultant vector is going to also have an x component, and the resultant vector is going to have a y component. Okay? Does everybody see that? Now, I think if you guys pay really close attention, do you guys see how this vector going up in that direction has a component? And let's write it in here. Would this be the ax component? And this be the ay component? Okay. Now, I think you guys are all in agreement. If that is totally horizontal, it doesn't have a y component, correct? So this one would just be what? Would bx equal 10 meters? Okay. And if we come over here, I'm trying to color code this thing, this would be cy, because it's going downward, and this would be cx. Okay? Now, if you guys would, I think you guys can see this. If I add head to tail, that vector, ax, that vector, bx, and then I come backwards, because this is a negative part, right? And I add that in there, would you guys see, can you guys see that ax plus bx plus cx equals rx? Are you guys seeing that? Okay. And then, additionally, ay is going that way. This doesn't have a y component. cy is coming down that way. And so if I add ay and cy, can you see how it gives me ry? Okay. So that's how I came up with this equation, or these equations. Okay. Now, if you were adding 6 vectors, you would just go plus dx plus ex, and you could just keep going. And this method works for as many vectors as you want to add. Okay. Austin.
I understand basically what you just taught, but I'm kind of having a difficult time conceptualizing the airplane thing. If you had an airplane, like say going like 45 degrees northeast, and then you had like the 25 meters per second of like wind going due east, would the airplane like be necessarily traveling at 25 meters per second due east along with the wind? Or would the wind have a limited amount of effect on the...
Let's do this really quickly, and then we'll revisit it if we can't get this. If you're flying like that,
Right.
and let's say you have a smaller crosswind like that.
Right.
Now, it's easier when we're at right angles to visualize, I think.
Right.
The plane direction would not be going that way.
Right.
It would be going in this direction right here.
Okay.
Yes. And
Okay.
because of the wind, okay, you would actually be going a little bit faster than you would if you wouldn't have the wind pushing you.
Okay.
Does that make sense?
Yes.
So, and you know, if we were going to real simple, let's say this was 4 and this was 3, just so because we know 3, 4, 5 triangles.
Right.
Then you'd actually be going 5 meters per second, and then you'd have to use trig to find that angle.
I guess I'm asking, like, would the 3 meters per second wind, like, cause the plane to be moving 3 meters per second east at the same time it's going 4 meters per second north? So it would be traveling the same speed as the wind in that direction.
Yep.
Okay.
Yep. And yeah, so the wind would be causing it to move in that direction. The thrust would be causing it to move in this direction.
Yeah.
Those two combined would then give it a...
Well, yeah, I understand
Lost
that. I just wasn't sure if, like, the plane would move at the same speed as the air in that direction.
And I think for right now, to keep it pretty simple so we can finish this and keep the video pretty short, and then we'll come back and talk about some of those questions, is I think about it in a river. Like if you were going across a river and the current was going down at 3 meters per second, your boat would be moving at 3 meters per second as you were thrusting across.
Right.
Does that kind of make sense?
Okay.
Okay. All right, so let's get rid of this and then we'll finish this up. Okay. Now we just got to find the components. Okay. Now finding the components, guys, here's what I would say. This is not hard. It's mostly just a keeping track of things sort of problem. Okay. So if we look at this, what is this AX going to be? Well, if we come back over here and we look at these components, this is like when you first start, I always have kids kind of set it up this way, but I think you'll soon realize that every time you set it up, you're either going to get a cosine or a sine function, and your unknown is always on the top. And so after I do these a while, I just start to realize that you're going to multiply those two together. And so to save space on this problem, when we look at AX, that is on what's, compared to this angle, is that the opposite? So we're going to be using what's trig function? Sine. And so this thing is going to equal the sine of 32 times what?
15.
Times its hypotenuse, which is 15. Probably should have done that in black. I got the wrong color there, but that's all right. And this AY here, guys, I'm going to go ahead and write this right here. AY, that is going to be adjacent, right? So that is going to be cosine 32 times 50. Everybody see that? Now in this case, that's positive and that is positive. So how I usually write it, and I'd ask you guys to do this, because if you make any mistakes on the test, I can figure out where that is. I would do this. AX is the sine of 32 times 15. Okay? And we know it's positive, so we're going to leave it positive. And then in this case, AY is going upward, and it's going to be cosine 32 times 15, and it's going to be positive. Everybody see that? Okay, so because it's positive, we don't have to put anything in there. And we'll look at the next one. Now, BX, which I'll try to do in blue, BX, well, B only has X component, right? And is it positive or negative? Positive. So we're going to put in here plus 10. And then here, because it doesn't have a Y component, just so you guys can see this in your notes, I'm going to put plus 0, because there is no Y component, because it's going due east, right? Then we'll switch over to the C. And guys, I think you guys are starting to see this. If this is 25 degrees right here, this is adjacent, right? This is the adjacent side. So we would have cosine 25 times, and then I guess I didn't write that in there, this is 8 meters. So it's cosine 25 times 8. And then this CX, right there, we're going to have the opposite, so that's going to be CX equals sine 25 times 8. The only thing that we're going to do different here, guys, is this is pointing downward, so that's going to be a negative. This is pointing to the left, so that's also going to be a negative. So what we would write here in our X component is minus, our X is going to be sine 25 times 8. And then here we're going to say minus cosine 25 times 8. Everybody cool? Now, this is where you got to do some math. Okay, so I'm going to rely on you guys to help me out. The RX component, can you guys go ahead and do that math for me on your calculator? Let's have this half of the class do that. And then this half of the class over there, let's do this component. And then we'll make sure we confer and we'll make sure we get the same answer. Okay? So you guys can do that. And while you do that, I'm going to do something here. Okay, does anybody have this number? 14.56.
Or 5, 7,
5, 6, 7, 8.
5, 6, 7, 8. That sounds good. We'll just go with that. Okay. And we got some verification. And guys, that's going to be in meters. Okay. And it's a positive. Okay. Which makes sense because is this positive direction here? Okay. And then what do we get here?
5.47.
5.47 meters. Okay. Which makes sense. It's positive. Is this going to be shorter than this guy? Yeah, everything's looking like it's working pretty well. Okay. Now, we have found the x component of our vector, of a resultant vector, and we found the y component of a resultant vector. Now, guys, it's simple math. We're going to use the Pythagorean Theorem. That squared plus that squared equals that squared. So what I've done is I've said r squared equals rx squared plus ry squared. And then to get r, we'd have the square root of, and in this case, rx is 14.5678 squared plus 5.47 squared. And we can find our resultant vector to be, I'll let you guys kind of work that,
15.56.
15.56 meters. And then, guys, how would we find the direction? How would we find that theta right there? Well, what do we know? We know, well, now we know all three of them, but mostly we know the opposite and the adjacent. So what we can do is we can say tangent of theta equals opposite, which is ry, which is 5.47, all over adjacent, which is 14.5678. In order to solve that, we're going to take the inverse tangent of the tangent theta equals inverse tangent of 5.47 all over 14.5678. And when we take that, we get theta equals we're going to take the inverse tangent of that.
20.7.
20.7 degrees. Now, if I've drawn this to scale, which I've done a pretty good job of, does that look like about a 20 degree angle or so? Okay. So our final answer, which I'm getting a little tight here, but this is my resultant, 15.56. So we'd put a comma and we'd say 20.7 degrees. And then what do we got going here, guys? We're moving north of what? East. So we would say n of e, and our resultant vector would be that right there. Okay? So that sums it up, guys. We learned how to break vectors into their components. We learned how to add vectors head to tail. And then we did a multiple vector addition problem using the components, breaking them down, adding them together to find the resultant, using the trig that we've been working on to ultimately find the direction of the vector as well. Okay. You can cut it, Brian.